Let's look at some conceptual models. They're very widely used in networking, and they're also very testable on the exam. If you're very new to networking, this will take a little time to get used to and understand. But if you are planning a career in IT security, just like you are on this SISM exam, you really need to know these. That way, when someone says it's a layer 3 problem, you don't just stand there with a blank look on your face, waiting for an explanation. The Open System Interconnect model, or OSI model, is a layered networking model that standardizes communication functions of our telecommunication or computer systems, regardless of our underlying structure and technology. That's quite a mouthful. What it really means is, model is agnostic of what you use of technology and applications. It breaks all the traffic down and then sends it over the internet. The OSI model has 7 layers. Layer 1, physical, 2, data link, 3, network, 4, transport, 5, session, 6, presentation, and layer 7 is the application layer. For the exam, I would know each of the layers, what they do, and their order. To remember it by, you can maybe use the all people seem to need data processing from layer 7 to layer 1, or from layer 1 to layer 7. Please do not throw sausage pizza away. When I did my certifications, I used layer 1 to 7. Please do not throw the sausage pizza away, but just pick one that works for you. This is one of the things when I did my certification, I wrote down on the paper before the exam started, and back then, it was a 6-hour exam, not the 3 hours it is now. Because realistically, I knew after 3 or 4 hours, my brain would be fried. I would not remember this. I would also know the PDUs, the protocol data units, for each layer. The PDUs for layer 1 are bits, layer 2 frames, layer 3 packets, layer 4 segments, and layer 5, 6, and 7, it's data. The OSI model is less commonly used now and often just used as a reference point, but for the exam, you definitely need to know it in and out. I know the graphics over here on the right might be tiny. That will be part of the PDFs you can download to help you with your certification. Layer 1 of the OSI model is the physical layer. That's our Ethernet cables, fibers, radio waves, hubs. Part of our NICs are networking cards, and the connectors on wireless. We can use copper and Ethernet cables here, twisted pair, and even more preferred shielded twisted pair, but they are also really secure. They're susceptible to eavesdropping, interference. They're easy to tap into, but they're commonly used because they're cheap. Fiber cables are much more secure. They're not susceptible to eavesdropping, but they're also harder to use. Since the core is a glass strand, they can break. You can bend them somewhat, but you can't turn them in a 90-degree angle with no ill effects, and they cost more. On layer 1 is also where we have our networking topologies. That's where our cables connect to our devices, and we can use bus, star, ring, or partial or full mesh topologies. We're going to cover all the topologies a little bit later. And the threats on layer 1 could be data emanations. People could steal our stuff. They could eavesdrop, sniff on our traffic, or just compromise availability with interference. Layer 2, or the data link layer, is what transport our traffic between 2 nodes on the same network. It uses link logical control for error detection. This is where we would have our MAC addresses, our BIA, burned-in addresses. MAC addresses are unique identifiers for each networking device, and it's embedded on our network cards. MAC addresses can be changed or spoofed really easily. And there can be really good reasons for that, or there can be really bad reasons for that. You just download a program and then enter the MAC address you want for your device. There's also been some cases when a networking device is made. Each of them should be assigned a unique address, so our networking devices know where to send the traffic. But in some cases that I know of, some manufacturer forgot that. So they send out a couple of 100,000 networking cards with exactly the same address. If you then get 2 or 3 of those on the local network, and since they're used to send local traffic, that will be a lot of confusion on late nights troubleshooting. MAC addresses can either be EUI or MAC 48 or 64. That just refers to how many hexadecimal characters. The 48-bit hexadecimal cards uses the first 24 bits as a manufacturer identifier and the last 24-bit as a unique identifier for that specific device. If you look on the graph over here on the right, you can see the 58-8D09 is unique identifier for that manufacturer, whereas the A554BA is a unique identifier for the device. Most, if not all, networking devices produced now use a 64-bit, where the first 24 bits are still the manufacturer identifier, but the last 40-bit are unique. We've realized that we have so many network devices that we just need more address space for the unique identifier for the device. IPv4 can use both 48 and 64-bit devices, whereas IPv6 only use 64-bit MAC addresses. If a device on our network only has a 48-bit MAC address, IPv6 will insert another 16 bits into the MAC address, making it a 64-bit EUI or MAC address. The most common threats on layer 2 are MAC spoofing, and MAC flooding. We just talked about the spoofing, and we'll cover the MAC flooding a little bit later. On layer 2, we also find that Address Resolution Protocol, or ARP, is considered a layer 2 and 3 protocol. Some of what it does happens on layer 2, some on layer 3. We also have CSMA-CD or CSMA-CA on layer 2. CSMA is the abbreviation of Carrier Sense Multiple Access. CD is collision detection. CA is collision avoidance. CSMA-CD is what we use for Ethernet and in most of our networks. The big problem with collision detection was that some of the older topologies only one node could send at a time, which then inherently made our network slow. We still use it. The way we avoid it now is we have a switch, where before we were using hubs. We'll look more both later, but what separates the two is the hub is one collision domain, and what the switches do is they segment each port from the switch onto its own collision domain. Since the traffic is just between one workstation and the switch port, there are no collisions. CSMA-CA, that's the collision avoidance, is what we use on our wireless. Wireless works somewhat similar to what hubs used to do, but technically only one can send and receive at a time. We'll dive more into that later in this domain. On layer 2, we would also have token passing. It's not really used anymore, and for the exam, you need to know it. It's used in some of the older topologies, and think of it similar to a talking stick. If you have the talking stick, you can talk. You're the computer that can send traffic. If you don't have it and someone else does, they can send traffic. You have the token that allows you to do stuff. On layer 3, the networking layer, this is where we jump beyond our local area network and onto the internet. Layer 3 uses IPs, and the internet is IP-based. And on layer 3, we isolate traffic into broadcast domains. Layer 3 pretty much has all the protocols that begin with I, which is an easy way to remember it. If at any point on the exam you get a question asking, which layer is this I protocol on, you can very safely answer layer 3 unless it's IMAP, which is layer 7. So really the only protocol I would bother remembering with an I is IMAP, it's layer 7. If it's not IMAP, it's layer 3. IP, ICMP, IPsec, IGMP, IGRP, IKE, ISACMP, IPX, all of those are layer 3 protocols, so instead of memorizing all those, just know IMAP is layer 7. Once we hit layer 3, there are also a lot more types of attacks. We have ping of death, ping floods, Smurf attacks, spoof source addresses, directed broadcast, IP modification, DHCP attacks, and many, many more. Layer 4 is the transport layer. We have briefly touched on SSL and TLS before. Both of those protocols range from layer 4 to layer 7. On layer 4, we have two main components, UDP and TCP. UDP, the User Datagram Protocol, is a connectionless protocol. It's unreliable, but it's used for anything we want in real time. We use it for our data, where timing is more important than the delivery confirmation that TCP has. And this is what we talked about earlier when we talked about voice over IP or video. Often UDP traffic is the ones that have the higher priority in our quality of service. We send the message and we don't care which order it arrives in, or even if it arrives at all. But maybe we do care, but the protocol doesn't. And the reason we do this is because we can't afford the overhead that delivery confirmation would add. If you're on the phone with someone and we had used TCP instead, the protocol might notice that 5 packets weren't delivered half a second ago and then resend them. Then those 5 packets would be added into the conversation, and either it would scramble it up so it sounds all weird, or it would wait until it received the packets in the right order and had all the packets. Then you'd have huge gaps in the conversation. So for anything where we need near real-time communications, we use UDP. And a common UDP attack is a fractal attack. It works similar to how a Smurf attack works, but it's often more successful because it uses UDP and not ICMP. In many places we allow UDP traffic, but it's common to block ICMP traffic. We'll look more at the attack later. TCP, or Transmission Control Protocol, is everything that UDP isn't. It's reliable. It's connection-oriented, guarantees delivery. It uses the 3-way handshake we looked at with SSL and TLS. You can see it over here, and for the exam again, I would know this. Client sends a SYN, server sends a SYN ACK, the client sends an ACK. But the TCP protocol is also a lot slower. It has a lot more overhead, and when data is sent, it's reassembled at the destination. And we use this for everything else that's not real-time traffic. Here the focus is getting all the data, regardless if it takes a quarter of a second more. If I go to ISC² website, I ask the server to send me the website information, and the server sends it. But the server also sequenced the packets. So on my end, I might receive packet 1, 2, 3, 4, and then 5 is missing. I'm then going to ask the server, hey, can you send packets 5 again? It then sends packets 5, it adds it in, packet 6, 7, 8, so on. Everything's reassembled in the order it was sent, and I see the full website. This could also be something more important. This could be banking information. So really for anything that doesn't need to be real time, we use TCP because it's reliable. The most common attack against TCP is SYN floods. This is where the client sends the SYN package, the server replies with SYN ACK, and then is sitting there waiting for the final ACK from the client. But it never sends it. Clients then sends thousands or hundreds of thousands of SYN requests. Since the server sits there waiting for the final ACK, it takes just a little bit of resources. Then when the client sends 1,000 or 100,000 SYNs, it can crash the server. For each layer of the OSI model, a little more information is added, or subtracted depending on which way we're going. Layer 1 is by far the fastest, and Layer 7 is by far the slowest. Layer 1 just has the data, whereas the higher we move up the OSI stack, the more information is tacked on to the packages of just data, and of course using more overhead. TCP uses 9 different flags to give more information about the package. These are called the control bits. We already talked about the SYN and the ACK package. The NS flag is a nonce flag. We will cover nonces more in domain 3. It's a random number we only use once. The way TCP sends packets is it sends as many as it can, regardless of the network connection. If the receiver is missing a lot of packets, the connection is throttled down until the send and receive kind of lines up and they agree on an acceptable interval to send the packages. If the receiver or the destination is missing a lot of packets, it can flip the ECE bit to tell we're missing too many packets here. Let's throttle down the connection. Maybe think of it as two people talking to each other. One party just keeps talking faster and faster and faster, and you can't really follow what they're saying, and it's really confusing. Then you tell the other party, hey, slow down, don't talk so fast, I can't understand what you're saying. That's basically what the TCP protocol does when it throttles down how fast it sends packets. TCP can also use the urge bit, which will notifies how urgent the packet is. PSH, push function, tells the receiver to push the buffer data to the receiving application. Then we have RST, which resets the TCP connection. FIN, that's the last packet sent from the sender, basically saying, this is everything I have, you have everything now. For the exam, I would understand how the throttling works, know the SYN, the ACK, the reset, and the FIN bits at least. Remember, it's reliable, connection-oriented, and all the packets are reassembled at the destination in the right order. And just like so many other things on the system, there's much more to TCP, but this is the level you need to know it at for the certification, and also to have a basic understanding of how TCP protocol works, what it does for us in our networks. I put layer 5 to 7 on the same slide because not so much is happening from our point of view on those layers. Layer 5 is the session layer. Session layer establishes the connections between our two applications, does the setup, the maintenance, and the teardown of the connection when we're done. On layer 6, the presentation layer, it does the formatting, the compressing, and the encryption on the file level for the data we send. This is also the only layer that really has no protocols. And then finally layer 7, the application layer, that's the layer that we see. That's where all the data is presented to the user. That could be the applications or the websites. That means it has all the application layer and the user protocols. This is where HTTP or HTTPS lives, because our website is on this layer. FTP, SNMTP, IMAP, and POP are email protocols. All those happen on this layer. As well as non-repudiation. Our certificates live here. Our application proxies. This is where we can do the deep packet inspection that we can't do on the lower layers if our data is encrypted. Remember, it doesn't get decrypted until layer 6, so at layer 7 we can look at the actual data inside the package. And this is also where we'd have our Active Directory integration. The threats to layer 5, 6, and 7 are also the same. Viruses, worms, trojans, buffer overflows, or vulnerabilities in our applications or our operating systems. This is the image I had earlier, slightly larger, but as I said, I'll also make it available in PDF in the download section. We can look a little at it here if we go to a website. Let's follow the website stream. On layer 7, I go to the website. That would either be HTTP or HTTPS. On layer 5, we would use port 80 or port 443. On layer 4, it's a TCP connection then, because we want all the data, we want it to be reliable. Then on layer 3, we either pick IPv4 or IPv6, and we could do Ethernet 2. On layer 2, then finally we could send our data out our Cat5 cables. So that's the traffic we requesting a website from a server would take to get to the server. Then the server would do the same in reverse. It would send the data out, their cables, over the Ethernet 2 protocol, use IPv4, TCP, port 443, HTTPS, and then finally the website would load on my machine. Layer 1, 2, and 3 are also referred to as the lower or the media layers, where 4, 5, 6, and 7 are the upper or the host layers. And it makes sense if you think about it. Layer 4, 5, 6, and 7 all happens on the local host, whereas 1, 2, and 3 does send the traffic over the internet or in our local network.